Dear participants, dear colleagues, we continue with afternoon session of our school, and it is my tremendous pleasure to inform you that our speaker in this session is Professor Alexander Sergienko from Boston University of United States. He is also a part of our institute, TÜBİTAK, Research Institute for Fundamental Sciences, as a distinguished associate member, which is a great pleasure and honor for us. He's going to give a lecture entitled, How to Engineer and Use Entangled Photon States. Alexander Sergienko received his Master of Science and PhD degrees in physics from Lomonosov, Moscow State University. Professor Alexander Sergienko pioneered the experimental development of practical quantum measurement techniques using entangled photon states. He is also especially well known for his contributions to quantum information processing, including quantum cryptography and communications, quantum networking, quantum imaging, as well as development of novel, ultra-precise optical measurement and characterization techniques, quantum metrology, which are based on the use of non-classical states of light. He's a fellow of Optical Society of America and a member of APS, the American Physics Society, and IEEE, the Institute for Electrical and Engineering. With this, I want to thank once again Professor Alexander Sergienko and invite him to the stage to begin his talk. Alexander, you're welcome to begin, please.
All right, well, thank you very much. Let me start sharing. Let's see. Hold on for a second. Just a second. I'll try to understand this. Hold it. Okay. Now I go here. Now I go. Just one moment. Okay. Can you see my slides?
Yes, it's perfect.
And the pointer also, right? The right
yeah,
pointer.
Yeah, sure.
Excellent. Thank you very much for the invitation to give this lecture. It's really a great pleasure to do that. And I understand that this part of your summer activities is devoted to more general audience of not only professionals, but also graduate students and other researchers who would be interested in learning more about basics of quantum optics. So that's why I selected the topic of entanglement for today's discussion, because entanglement today is at the heart of everything. In quantum information and quantum optics. In fact, that's a major resource that is available to us in quantum information processing. And I also wanted to point out that it's not only a subject of research studies. In fact, it was under the research studies for so many years now, for about like 35, 40 years. It became a very useful resource that can be used to do something useful. And the question is what it is and how to do that. And that's why I want to discuss how to engineer and how to use entangled photon states. So I will be talking about the entanglement in electromagnetic field, not entanglement in spins, not entanglement in superconducting currents. This is all about photons. Photons are excitations of electromagnetic field, and that would be the subject of our discussion today. So first question is, what is entanglement? Well, it has been introduced a long time ago Basically, Schrödinger called it entwinement. It's more like if you have two particles, you cannot really separate them. They form some kind of entity that is inseparable. And in terms of quantum mechanics, what does it mean separable or non-separable? So if you have a wave function of two particles, A and B, then it's separable when you can present it as the product of two. And well, the rest here is just for the other cases. So, and they are entangled when this is not true. Whenever this equality is not valid, then people call it entangled. So you cannot represent it as two independent particles. That's the first definition. Many people know about that. But well, and that's where stories started many years ago. And people looked at that and started from Einstein, Podolsky, Rosen. They analyzed this behavior. There's unusual properties it can provide when you try to use it in experiment. Well, of course, they created the Gedanken experiment, where the entangled photon state has been created at two space-time separated points, and by the measurements, it resulted in some outcomes that they consider to be not very realistic. That's why they bring the issue of physical reality and completeness of quantum mechanics. Well, I have to make a comment here that they call it, and people call it like Einstein-Podolsky-Rosen paradox. In reality, there is no paradox there. Einstein-Podolsky-Rosen just, they did not point out where this entangled state has been created and how it's been delivered to the point of observation. Basically, they left out the process of creation outside their model, and that's really kind of violated one of the major postulates of quantum mechanics, that you're not supposed to bring the energy inside your system from outside. If you include the source and delivery of the state to the points of observation, the paradox just goes away, and it's so fully described by quantum mechanics. But it's a valuable resource, and when you analyze what kind of properties it delivers to observer, of course, after you create it, after you deliver to observers, then you can treat it as from the standpoint of information. So Schrödinger was saying that for an entangled state is the best possible knowledge of the whole does not include the best possible knowledge of its parts, because they are connected. You cannot learn about parts without taking full information about state from both sides. By the way, it is important note. So, you know, sometimes people saying that if we're like interpreting Einstein-Podolsky-Rosen paradox, like if I detect one particle, I know about the other one. It's not correct. You have to detect both particles, then you know what it is, the full information. Well, entanglement is a fundamental resource of nature, comparable to energy, information, entropy, or any other fundamental resource. And this is Nielsen and Chuang, the authors of the famous book about quantum computing. It highlights the issue that entanglement is a resource for quantum information processing, very valuable resource. Majority of quantum information procedures are based on the use of entanglement. Well, there are many other later famous researchers were looking at this entanglement and treating it from their own perspectives. You see, like Mermin always been interested in foundations of quantum mechanics, so he comments on this, a correlation that contradicts the theory of elements of reality. John Bell was talking about the correlation that is stronger than any classical correlation. Remember this because it will be interesting. I will talk about this classical versus quantum correlation in a minute. A trick that quantum magicians use to produce phenomena that cannot be imitated by classical magicians. Asher Paris was a great scientist and with a good sense of humor. I guess that's what he put in here. Well, Charlie Bennett illustrated this as a resource for some quantum information procedures, such as quantum teleportation. But not only that, many others as well are based on entanglement. Global structure of the wave function that allows for faster algorithms. Well, of course, Peter Shor's algorithm is based on the sequence of control NOT gates based on executing quantum Fourier transform that is based on entanglement always. Arthur Eckert built up a quantum communication, secure quantum communication principle, the Eckert protocol based on entangled states. Well, and of course, on the highly mathematical application of this in the Horodecki family commented the need for first applications of positive maps in physics. This is really mathematicians' view on the subject. So, what is the entanglement? What its relationship with correlation? And I want to point this out because lately there were some discussions about the classical entanglement and so on. And let's just make clear kind of notions, clear up this issue here. So if you have two systems, A and B, and you want to consider the system C that is joint of A and B. Well, what is the correlation and what is the entanglement? So as I mentioned to you, entanglement, it's an inseparability of the joint function. Well, inseparability, it's a purely mathematical term, and it's applicable to so many functions in this world. There are tons of different functions that can be inseparable. For example, the classical probability P of C for two systems that are correlated, it's also inseparable. That's a formal definition of classical correlation, inseparability. But this is not the entanglement in the meaning that Schrödinger introduced that. The entanglement was introduced as a quantum entanglement. What's the difference between quantum and classical in this case? The function, the wave function, to which the entanglement term it relates to in this aspect in quantum mechanics is the function of probability and amplitude of quantum state, psi A and psi B. So when the inseparability is applied to the wave function, that's what the quantum entanglement is about. And I hope you all understand what's the difference between the wave function and probability function. Probability, it's a classical function there, it's already square of the wave functions. It's like its amplitudes, and probabilities are complex squares of that. So calling the correlation and inseparability of that function as the entanglement, well, in principle you can, because you could say, oh, that's inseparability, but it's a classical probabilities, it's a classical effect. When you want a quantum entanglement, you have to look at the wave function. Wave function is amplitudes and phases, and when they are inseparable, that's what the quantum entanglement is about, and that's what we will be talking about. And really, people need this. This is the quantum resource. Well, in terms of photons, so you can have this is the examples, one of the example of inseparable entangled states that could be realized in quantum information processing. It's a function of two qubits, so two photons, and they are in the superposition state. So as you can see, it could be one photon in zero state, 1 and 1, minus 1 and 0, and so on. So as you can see, all these functions are inseparable. You cannot represent them as a function of something of x product with y. It's always superposition. And we'll talk in a minute, what does it mean for the quantum engineer if you would like to make such a state. So let's just ask then the question how we can make entangled states that are needed for any quantum information processing or quantum measurement, quantum sensing, and any other quantum imaging, any other applications like that. So please pay attention to this correlation plus superposition. That's, as I usually call, the two conditions that you need to satisfy, and I'll talk about this in a minute. What does it mean? So if we go to the Einstein-Podolsky-Rosen paper, and if we ask if we can see the joint function of two particles x1, x2, then you will see this is the bilinear superposition, superposition of bilinear terms, infinite one. You see, like from n equal 1 to infinity. So since it's a superposition of bilinear terms, it's not factorable in this particular case. David Bohm in 50s did a great job explaining the nature of entanglement by taking the spin up and spin down, two particles with spins. So each particle can have spin up or spin down. And 1 and 2 is symbols of the particles. Particle 1, particle 2, particle 1, particle 2. Just let's look at this and ask ourselves, what does it mean, this formula physically, for experimentalists, for physicists, for engineer? So what it tells you two things. First of all, there are two options, option 1 and option 2. And these two options are absolutely indistinguishable. They are equal. So it could be either one or another one, and the weights of this, the weight coefficient is exactly the same. They are absolutely indistinguishable. This is called superposition. Basically, that's a definition of the superposition. Either this or that, and you cannot make a distinction between them. That's the first condition, superposition. Second one is, you see, there is this sign between these two terms. It could be minus, it could be plus, but it must be stable. When you have some stable relationship between two terms in the wave function, it simply means there is a stable phase relationship between them. So in principle, you can put here e to the I phi term, and when phi is fixed, like mine, basically, when phi is like e to the minus pi over 2 or pi, so this sign will be fixed, either minus or plus, but it has to be fixed. So when you have two events, two outcomes, and there is a stable phase relationship between them, this is the definition of correlation, or coherence, actually. Coherence, it's when you take something, like in electromagnetic field, two spatially separated point or two temporally separated point, and if there is a stable phase between them, then these 2 points considered to be coherent. How to reveal the coherence? You have to do experimental measurements, and you reveal it through the correlation. You measure field here, you measure field here, compare them in correlation, and see what it is. So I use the term correlation as the experimental evidence of coherence. So you need superposition and coherence, or superposition and correlation, and that's what you need to build up entanglement. So what type of entanglement you can build up with optical states? It could be polarization entanglement, for example, HV plus minus VH, like one photon is vertical, second horizontal, then vice versa, horizontal, vertical, and stable phase relation between them, plus or minus. It could be phase of the photons going in the interferometers. I'll show you later on an example of that. It could be short, or long path of the interferometer, but it has to be a superposition of two, and they have to be indistinguishable between each other. This option have to be absolutely indistinguishable. That's how you build up superposition. One more comment I would like to make using this type of entangled state. You could find this in many textbooks and many papers everywhere around in quantum information. You see 0, 1, 1, 0, 0, 1, 1, 0, and so on. First of all, this is logical 0 and logical 1. They are associated with the binary algebra of qubits and so on. From the and you see they all valid non-separable states that are called entangled states. I want to point out one issue that sometimes is overlooked by theoreticians, but very important for experimental realization of entanglement. Whenever you see 0 here, it's 0 means logical 0. It doesn't mean empty, because in order to detect something that it carries 0, you have to have energy in that state. For example, it could be, for example, 0 and 1 could be two energy levels of atom, ground state and excited state, 0 and 1. In our case, in optics, it's very often, well, it could be spin up and down. For example, down is 0, up is 1. In photons, it could be polarization, horizontal polarization and vertical, but you always have energy associated with that, because at the end you have to detect this in correlation and see which term of this superposition you really have, left or right. Okay, so the point is every logical bit, a qubit or state here, every logical state must have physical implementation behind that carries energy that can be detected and give you information about this state. Was it 0 or was it 1? All right, so that's we come in here to the generation of Bell states, and I would like to, this is my last comment is mainly applicable to this situation. Sometimes people say, oh, we can have a single photon entanglement. We can put a photon at the 50-50 beam splitter, single photon, and what we have? We have either photon goes to the right and nothing goes to the left, or vice versa. Well, what is the problem with that? The problem with that when you have 1 here, you have energy of the photon. When you have 0 here, it's empty arm. You don't know what's in there. And in this case, this term doesn't have a definite phase. So then this configuration really will just fold into the product, because this phase here will be arbitrary because of it's attached to the term with no energy here. It's like a vacuum port basically of your interferometer. When you have 1, you can detect it and you can see what was the phase of this photon, but 0 doesn't have any definite phase. So that's an important point for anyone who would like to make entanglement. Always make sure that your logical entanglement is supported by energy carrying physical parameter. All right, so now how to make it? The first source of of course, one of the first sources of entanglement was atomic cascade decay that Alan Aspey used for his Bell tests. When you have 2-photon transition, and this 2-photon transition can be made of 2 photons of opposite polarizations, either HV or VH. But the problem was purely practical. So if you have an atom, everything goes in 4 pi, because momentum can be conserved in every direction. So if you try to do experiment, you have to really hard time to collect those photons, and you have to wait for a very long time. So that's why people turn to spontaneous parametric down conversion. By the way, I put it here that it's also known as parametric fluorescence, parametric luminescence, or parametric scattering. That's what really 3 names of this process originally, until Len Mendel in 1985 introduced the term parametric down conversion, which originally was designed for different nonlinear processes, but by adding term spontaneous, it became common term for the process we're using today. So what it is, it has the nonlinear crystal, it has the pump. just a second. I just want to, I cannot see the time on my computer to understand. Hold on for a second. On the second. Hold on. Can I ask you please, Alikram, could you give me 10 minutes warning before the end, because I cannot see the time right now on my when I'm
okay, no problem. No
10
problem.
minutes.
Okay. Okay, no problem. Please continue.
Yeah. It's a process inside nonlinear crystal. You put a pump radiation and you have two photons, signal and idler. This is the pictorial expression of that. So K power, momentum conservation, energy conservation has to be satisfied to do this. And that's what it looked like. You have two directions. That
Can you please enlarge your slide?
Oops, sorry. I didn't hold it. Just a second. Stop sharing. Hold it this. Sure. What? Oh, okay. It's this, this, this, this. Is it okay now?
Yeah, it's okay.
Yeah, sorry about that. Basically, there are these two photons that are coming, they are correlated. They're correlated in time, they correlated in direction, they correlated in energy, and they correlated in polarization. So you have all the like 4 types of correlations associated with these photons, and the momentum energy conservation here. When someone was saying, oh, in this nonlinear process, you have momentum energy conservation, this is the particle physics approach to the process. If you do in nonlinear optics, you know that inside the nonlinear material, these two equations are not independent anymore. They are connected through the refractive indexes. So NO and NE, and this is really a phase velocity relationship, phase velocity matching. That's what's called a phase matching in nonlinear optics. So that's what needs to be done. And what result is 2 types of parametric down conversion, type 1 and type 2. What it means type 1? Type 1 means that both photons are going out or have the same polarization, and type 2 means that they have orthogonal polarization. And they come up in a different way. When they have the same polarization, it's like circles if you look inside the crystal. And the photons always on the opposite sides of the center, because momentum is conserved. When this is plus K, this was minus K, plus K, minus K, and so on. And the colors of this also complementary. I'll show you in a minute. And type 2 is a little bit more difficult, but still the pump radiation is going right here in the middle. And all the rest is symmetric relative to this point. You see the photon 1 is on the same distance as this one. Its momentum is conserved. The same is here and everywhere else. So what you have in fact a hyperentanglement, or possibility for hyperentanglement between polarization, frequency, because frequency like omega 1, omega 2, then you move to this point, it will be 1 omega, another omega. All these omegas are correlated. And this is the Q, it's a transverse K vector, it's a directionality, also correlated. So they happen to be concurrently here. But for now, we talk only about correlation. Superposition will come in a moment, and we'll discuss how to design. So if you have type 1 down conversion, that's what it looked like in real experiment, when you basically try to look into the crystal. Of course, you have to make a beam stop right here to stop the powerful laser to make sure it does not overwhelm your sensor. Just don't try to do it with your eye. This is the camera. Because the intensity of down conversion obviously is significantly lower than the intensity of laser light. You have to block it. So what it looked like is, let me show you a brief kind of visualization of the process. So we can have a laser, nonlinear crystal, and this is just a screen. And you see the photons are coming out in pairs. Those pairs are always on the opposite side of the center of the laser beam. Their colors complementary. The energy of this photon plus energy of this photon should be the energy equal to the energy of the pump photon. And you have to keep the relatively low power of that laser, so they come with well-distinguished pairs, because you have to make sure you distinguish one pair from another, from another, from another, because that's how you detect separate quantum systems. The minute these two photons start to overlap and you cannot distinguish them, when you have too many of them, for example, you lose your quantum properties, and you'll see this in a moment. So basically, if you have these pairs here, and now if you switch your power higher, for example, if you increase the power from low to high, that will happen, I guess, in the moment. You see now it's high power, there are many of them, and now you will have a hard time to detect separate states. You will run into the classical regime of the overlap of the mixture of the quantum states. Okay, so that was the type 1 down conversion. Everything what you need, what you have there, you have correlation, you have perfect correlation of direction, energy, time, and polarization. But as we discussed, for the entanglement, you need not only correlation, you need superposition. How to do superposition, and that's where the type 2 phase matching was critical for that. That's what we did so many years ago for the first time. In 1994, actually, this picture was taken. At that time, by the way, there were no color sensitive cameras to take it, so it was black and white picture, and it was color, it was just a color pens. Nowadays, color cameras can detect it directly. So let me show you how it works. Again, it's better to see it one time than to hear about that. So type 2 down conversion, how it works. You have a laser, nonlinear crystal, and now you have two rings, one for ordinary polarized or vertically polarized light, and second one for the horizontally polarized. And these pairs of photons are coming on the opposite sides of the laser beam because momentum is conserved. Their colors complementary to have together energy of the photon of the laser, and you can see horizontal and vertical polarization attached to them. So they are correlated, but there is no superposition yet. We need to satisfy the condition of superposition to create the entangled states. How to do that? Well, we need to do a very, very simple trick. And the trick is to tilt the nonlinear crystal. And you will see what will happen when we start tilting the nonlinear crystal. So if we start tilting this, you see the rings starts to overlap. So now there are two regions here and there where you have complete superposition or indistinguishability of photons. On the left, it's same color, green, green. The distance from the center is the same, so its k vectors are the same. And we can try to cut these two areas right here. And now when pair comes through, you don't know, was this from the top or from the bottom, and on the other side, the same thing. That's how, but if it's vertical on one side, it should be horizontal on the other side, and vice versa. So that's how you create the entangled photon states, is in polarization. It's vertical horizontal or horizontal vertical with 50% probability. Now let's try to detect it and verify it. So if I put a polarizer at 45 degrees in one of them, then as always, because it's 45 degrees analyzer, it's 50% of time it allows photon to go through and 50% not. But then we put a second polarizer here at the same angle, 45, 45, 2 photon counting detectors and coincidence circuit. And let's see what happens. Now you discover that it's always one goes through, second not. There is no coincidences in here. And what we can do, we can try to rotate one of the analyzers 90 degrees away. Now it's plus 45, minus 45. And what happens is they either both not going or they both passing by and giving you coincidences. So this is nothing else than the apparatus for observing Bell's inequality violation. How you do that? You start to rotate the second polarizer continuously and watch for the behavior of coincidences. On the vertical axis, this is number of coincidences. This is the angle of the second polarizer. And as you can see, it traces cosine square waveform of interference between polarizations. And if you have if the visibility of this curve is 100% or close to 100%, that's a proof that your state here is polarization entangled state. In fact, that's how you would use this. Oops, so I'm sorry. That's how you would use this entanglement. So originally, this has been used to verify that you created the entangled state. The Bell's inequality test is the one that tells you whether you have entanglement or not. How it will tell you? It will tell you depending on the visibility of this curve. If this curve has a close to 100% visibility, it's entangled. If it's going below like 72%, it's a classical state. So also, well, this is how it's historically been done, and now this Bell's inequality violation, it's a procedure just of aligning the source. You create a source of entanglement in polarization, you immediately do this just to verify how good is your entanglement. Can you use it, or you have to improve your source? So the easiest application of this could be so to try to do quantum communication or secure quantum cryptography. If you have these two beams of entanglement, HVVH, we can keep one beam with Alice and give the second beam to Bob and do the measurement of coincidences, Bell's inequality measurements. Then we can see if anyone has been interfering with the state during the propagation. Because in quantum mechanics, when you create the state, you propagate state, and until you detect the state, it's a quantum system. It's isolated. It has to be isolated quantum system. If someone touches this quantum system on the way, it destroys these properties and immediately it goes in the classical domain. So you will not be able to violate Bell's inequality anymore. And this serves as the indicator someone was tampering with your communication line. Well, for example, in Boston many years ago, in around 2003, 2005, we built up such a system in Boston. It was the DARPA quantum network between BBN Technologies, Harvard, and Boston University. In commercial fiber inside the city, this system was running continuously for 3 years. And just want to point out how much was developed in 90s and 2000 before the new wave of interest to quantum came about 10, 12 years later. Okay, so how else you can make the entanglement? Because using the crystal, tilting the crystal is a little bit inconvenient from the engineering standpoint. You want to have the parametric down conversion in conditions that are easily to implement. So what is the usual problem? So you need the phase matching. If you try to do something in the collinear case, so you have K of the pump, you have K signal, K idler. But if you take any material and just put it in, you will discover that phase matching is not satisfied. That's really why originally you have to rotate your crystal around and find the condition where it's really satisfied. You always will have this deficiency from here to here, this white vector, it will be missing. Oops, sorry. This vector will be missing. And the question is how to fill up this gap and satisfy this condition. The idea really is very old. It belongs to Blombergen and his team, and it has been published first time in 1962. It is called periodical modulation of nonlinear susceptibility of nonlinear crystals. And that's what it is. You create layers of Chi2 axis up, Chi2 axis down, up, down, up, down, and this create this missing vector K. And the point is, it's in your own hands to design how big is the period, what is the periodicity of this, so you can tune up this vector K to match this gap, to bridge the gap and satisfy phase matching. So now you don't have to rotate your crystal, you just cut any orientation and calculate how much is missing and pole it in this fashion, and you can have it go in effectively parametric down conversion. These are examples what can be done. And the other interesting thing is in natural down conversion, in the natural birefringent crystals, you always have to have one of the waves to be opposite polarization from two others. In type 1 will be ordinary and extraordinary, extraordinary, or type 2 will be ordinary and ordinary, extraordinary. You never can have polarizations to be the same for all waves because you cannot close the gap naturally. But when you do it artificially like this, you can have that. And I will show you why this is important. EEE or type 0 parametric down conversion. So this is what it looks like when you pull your nonlinear crystals. You just make periodic structure. This is like period of 13 microns. Then you take this crystal, you put metal layers, those layers right here, it's metals, and substrate here is lithium niobate. And you put this inside the bath with the liquid electrolyte, and then you put a high voltage to around 20 kilovolts, up to the 20 kilovolts. So this is the shape. You start to increase it, you keep it, and then you decrease it. What happens when you put so high voltage, because nonlinear crystal is ionic crystal, the ions get shifted. And what happens then, you create you reorient lithium in the crystal lattice, and it changes the orientation of the optical axis. So what you have this structure, periodically poled lithium niobate, you have pump, and now you can have multiple interactions going on. Why I told you about the EEE is the good one, because look here, this is nonlinear coefficients that tell you how efficient the process is. And this process is significantly more efficient than any of the naturally occurring in the nonlinear crystals. That's why it's nice to use it, because you gain in the efficiency of the pairs, quantum pairs production, correlated pairs production in comparison to the bulk material. So what you can do, as you can see, so you can look at there, you can see all these rings. For example, you put polar analyzer along one axis, you see internal ring right here. You put it on the other one, it's external ring. So it's really type 2 down conversion, as you can see. This is one polarization and this is opposite polarization. Well, another tool is, since we have a periodic modulation of the nonlinear material, every periodic structure can have subharmonics, and you can have these interactions to be satisfied with different periods. Although when you go to higher harmonics, your efficiency is dropping. So it's just a nice engineering tool. So basically what you also have, you have a temperature. Temperature of the lithium niobate here is the tool to change the position of those rings. And here you can see there are so many interactions. Like if you have Y like polarizer along Y, you can see there are two of them. There are two interactions going simultaneously at different frequencies. So if you really want to select them, you have to select frequency and polarization together. And so that's why like all different types of interactions. What you can do, what it helps you to do, for example, if you take interactions such that one of the photons at 110 nanometers, another one at 1550, you can try to design entangled quantum cryptography communication lines such as Alice would work with visible photon, and to send photon to Bob, you can use fiber, because 1550 is a fiber communication line wavelength, and you can send it over long distance. That's what you have heard probably in the literature and many times, that the distance for quantum communication could be tens of kilometers. Well, when you go to hundreds of kilometers, it becomes problematic because you cannot cancel losses. And the loss is the major problem for quantum communication. Single photons and quantum states, they cannot be re-amplified. So when you start losing them, it reduces the intensity or speed of this quantum cryptography. Unfortunately, all the records that you see published, like 500 kilometers, 400 kilometers of quantum cryptography, always look at the end. What is the rate of secure bits communication? Unfortunately, it will be just either 1, 2, or very often it's 0.1, 0.01. And it means not very practical, unfortunately, over long distances. For quantum cryptography, like in the fiber, the reasonable distance would be like 30, 50 kilometers. This is metropolitan city. All right, so one other type of entanglement, remember, what do we need? We need correlation and superposition. So you've heard maybe about the Franson interferometer. It's a famous design. So you have a source of correlated photons. One goes to the left, one goes to the right. So correlation is there. You have to make superposition. And to make superposition, you have two unbalanced interferometers. And when photon comes in, it can go either long path or short path. So basically, when you try to measure coincidences on both sides, it illustrates that photon can go through the short and long. They are indistinguishable because distance between these two events is 0. When you go across terms, long short or short long, there is time either plus or minus at later earlier arrival of the photons to the photodetectors. So, but if you can cut this central part and ignore this one, then you will preserve indistinguishability by virtue of filtering information. Just it's a little bit artificial, but a result is exactly the same as if you would have the original entanglement. And it's used many times in many different areas. I just want to point out, in our research, we usually call it operational entanglement. When you have natural entanglement, like in the previous case, as I told you about the polarization entanglement, when you send it from the crystal to two different users, you don't need to say anything. You just say, okay, here I'm sending you entanglement and polarization, measure it. And they do polarization measurement and evaluate. Here, you have to say something else. You have to give instruction how to observe it, what observer has to do to really get the result. You have to say, oh, look only within this time interval relative to 0 and ignore all the events outside. And if you do that, you will have exactly the same effect as before. So let me just show you how it works. Just introduction. So Franson interferometer. So again, we have the laser nonlinear crystal here, and we have these two correlated beams. So they are symmetrically positioned relative to the center, and there are two interferometers, one here and one here. You see, with two detectors, D1, D1, D2, D2, and there is the coincidence circuit on the right. And basically, these photons can statistically go in different routes through the system. Pardon? Okay, and so these photons go in, can go different paths, and sometimes when they arrive simultaneously, the coincidences goes on. So basically, it's short, short, long, long, short, long, and long, short photons. And when you have mixed ones, there is a time difference. When there are short, short, long, long, there is no difference. So we can start looking for the number of coincidences and their positioning in time, as you can see. So when it's long, long, short, short, we can keep adding along this line of zero delays. And these two guys, long, short, and short, long, they are with plus delta t and minus delta t. And at the end, after some time, you would see the distribution of coincidences when the central peak will be twice higher than the neighboring ones, because it has two probabilities and each one of neighbors has one. Basically now we can narrow the coincidence window to include only long, long, and short, short. And now we can try to observe the behavior of this peak when we try to make the change in one of the interferometers. We change the phase inside the interferometer. You see, when both arms are absolutely identical, the coincidence count is at the maximum. They always give you coincidences. So they go short, short, give you coincidences, long, long, gives you coincidences. So you are here at the peak of the coincidences.
Alexander, 10 minutes.
Okay, thank you. Oops, sorry. Just a second. Okay, we narrow the coincidences. So then we have the, let me see, phi 1, phi 2 are the path length through the lower upper interferometers. So we, well, we'll just, I'll pass this one. So if we move the phase to half of the, change basically the sign between the terms, we go to the 50% coincidences here. So the peak is at 50%. And then we can change phase further and we can move it really to the bottom, which means by continuously changing the phase and observing only central portion, we can have from 100 to 0% modulation of the visibility of the coincidence pattern. That's exactly what we need for the Bell's inequality. We can see what happens when we open the window, permitting the wide coincidence window, which includes long, short, and short, long coincidences, and then no subject, they are not subject of interference. So they create a background now. And this background reduces overall visibility here to 50%. You see now all three peaks are included and visibility is 50%, and it's not different from classical one. So what we have here is a demonstration of operational entanglement creation. By narrowing down the window, we create the situation that observers see exactly the same as if they were given true entangled states. So when you open up the window, then it becomes classical state. So it just highlights the power of entangled state engineering, that if you understand what you need, when you need the correlation, and then you need superposition. When your superposition is not complete, you have a choice. You have a, as an engineer, you can try to cut only equal portions that are absolutely indistinguishable, and that becomes the tool for entanglement engineering. Okay, what else you can do with that? And by the way, another small brief version of entanglement engineering. Let's go to the type 2 collinear, when two photons go in one single direction. So they are correlated by polarization, but there is no superposition. The great thing in optics is superposition is very easy to obtain. You put a beam splitter. Beam splitter takes one thing and creates two equal, like 50-50 beam splitter, two equal options. And that's what the superposition needs to have. For example, if you have nonlinear crystal, this is the beam splitter, this is two detectors, two polarization analyzers in front of them, and this is the birefringent delay line. This birefringent delay line just delays one horizontal versus vertical photons arriving to the beam splitter. So if you have these two correlated photons originally coming to the beam splitter, you have four terms here. Oops, sorry, you have just four terms, which is classical state. To have the entanglement is only top here. You see HV minus VH. These terms are not needed. You have to remove them. How you remove them? Oh, you just observe the coincidences. Simple observation of coincidences removes terms where you have zero in one arm and energy in the other one, because this physically cannot create coincidences. So basically, by fact of observing these incoincidences, just you create this entangled state, and you have the very nice correlation with coincidences going from zero to the maximum and back. So that's another way of entanglement engineering, and it becomes very useful. You know about the Horn-O'Mandel interference on the beam splitter. This is its polarization counterpart. So if you have your correlation dip, then if you put some sample inside here, and this sample introduces a little bit of birefringence, that your dip here will be moving. So it's a delta due to the sample. So this becomes immediately a sensor of very weak slide birefringences using this apparatus. And this is another branch of quantum metrology. It's a quantum sensing of delays and so on. Well, now, in all quantum states engineering, as I told you, there are three stages: creation, propagation, and detection. So creation, we discuss sources. Propagation, we also discuss how propagation and altering propagation can change the state that will be detected as entangled or not entangled. Now, detection. Detection is very important part of quantum procedures. So if you have coherent states and you just put optical attenuator, then you have a weak coherent state. Weak coherent state, when it comes like one photon at a time, it's also sometimes people call it quantum state, but it's just a Poisson distribution of photons in time. When you have a correlated two photon states, then like from SPDC coming here, and if you have a single photon detector, then you can create a situation when you detect the photon, you know immediately there is a twin brother traveling in this branch, and you can create an optical gate that is driven by the action of this detector. You open it up, the photon comes through, you close it up before the next one. So you have a heralded source. Basically, this detector is a herald, it heralds it and closes the source. But still, the SPDC itself is a spontaneous process. It's still Poissonian. So sometimes you have not one pair, but you can have two pairs coming out of the SPDC, and it's not good. For example, for quantum cryptography, you need to have only one state, not two states simultaneously. So for that purpose, if you have photon number resolving detectors right here, that's an ultimate detection of the quantum states. It can tell you no photon, one photon, two photons. And for example, if it tells you only one photon was in this state, then you open it up, close, and then you know only one photon travels in this direction. So That's the ultimate goal of the photon of detection in any quantum optical experiments. How it can be done? It can be done using transition age sensor. It's a superconducting device, which really is sensitive to the energy of single photons coming in. And you can detect it. When 2 photons coming in, you have twice the energy, 3 photons, 3 times the energy. That's what, like you can see how like 1 photon, 2 photon, 3 photon, 4, 5, 6, 7, 8, 9, 10, and so on. That's from our original paper with John Martinez and Seivunam a long time ago. And what you can do with that, and this is what the system looks like. It's in my lab at BU. So this is the refrigerator where the transition edge sensor staying, and the system, optical system, is under this cover there. This is 4 superconducting detectors, and basically you can detect 1, 2, or 3 photons probability. For 1 and 2, you can have the clear separation between them. And the question is, what you can do with that? And the first thing came up is, we all know Hongo-Mandel experiment. Hongo-Mandel experiment always tells you, oh, you have a dip, and because you don't have any coincidences here, it means 2 photons goes to the right or 2 photons goes to the left and nothing in the opposite branch. That's why there is no coincidences. Now, we had experimental verification of that at that time. I guess it's already like 20 years ago. So you have photon number resolving detectors. So blue one is a coincidences 1 and 1. That's a normal coincidences that you will see in Hongo-Mandel experiment, and obviously they show the dip. But are not 0, 2, it's on one side, 2, 0, it's on the other side. You would see that directly when you have deep in single photon coincidences, you have 2 peaks in 2 photon detection in the 2 branches. And the probabilities of each one here is 1/2 of this one. So that's exactly what the direct observation of Hongo-Mandel with direct detection of all terms participating in the process. Well, and also, in addition to the transition edge sensor detectors, there are superconducting nanowire detectors that came originally from the Professor Goldsman's group in Moscow. He invented this, and they are now widely used everywhere. These detectors are fantastic because they have extremely broad detection efficiency, from visible to infrared, which is not possible with any semiconductor devices because band gap is not here. So you can detect any bandwidth. For any broadband application, it's incredibly good device, and it's based on the effect of the hotspot. So you have superconductor, the photon comes in, breaks superconductivity in a very local space, then it heats up and starts pushing current out. But because it's pushing current out, it heats up even more there. There is a chain, avalanche of heating up, and then the superconductivity breaks here. When superconductivity breaks, resistance increases and it creates a voltage pulse. And then, because it's all in the cryostat, in superconducting cryostat, this energy goes away and it recovers its original state. That's how you make a pulse of the voltage for detecting those effects. And as you can see, these devices were invented back in 2001. Now everyone is using this in quantum optics. And this just shows you at different wavelengths how the coincidences curves are used. And they are extremely nice devices for the use in the infrared. In quantum cryptography with telecom wavelengths, everyone is using superconducting detectors because you cannot do anything about that. The indium gallium arsenide detectors are too noisy. So that's how you use them. You just the old-time use of this. You take the detector, you drop it in the liquid helium, and that's how you use it. The tiny things in there, it's 10 by 10 or 3 by 3 microns spot, and then fiber takes your light in, and the electrical wire takes the electrical signal out. Today, these detectors are used in very often used without liquid helium, especially because liquid helium is getting so expensive. So more and more popular systems without liquid coolants. It's a closed cycle refrigerator based on the Stirling cooling cycle, just mechanical, and it becomes a widespread equipment for quantum information processing. All right, so with this, I would like to stop. Thank you for your attention. If you want to see more applications of entanglement in different areas of metrology, imaging, and communication, there are some of them in our recent book, or just visit my website, go to the publication sections, and you will find lots of applications over the last 25 years. Some of them even people today start to reinvent and come back to that. Some of them are still waiting to be reinvented, but you can go directly to the original source and see that. Okay, thank you very much. That's all what I have today.
Thank you very much, Alexander, for this very excellent lecture. Can we now take some questions?
Yes, yes, please. I'll be happy to answer.
Yeah, please ask questions. Alexander, can you read questions yourself, or shall I read for you?
In the chat, you mean? Yes,
yeah, in the chat. Özgür Hocam buyurun. Özgür Hocam, you're welcome.
So here's the question about the difference between parametric down conversion and parametric converter. That's exactly what I mentioned in the beginning, that parametric conversion, optical parametric conversion started in early 60s, immediately after the discovery of laser. People were trying to develop laser-like sources with tunable wavelengths, and they design up converters, down converters. All this has been used. And when the effect we're talking about appeared, it had names of parametric fluorescence, luminescence, and scattering of light. Why I'm saying these three, because it has been discovered in practice experiment in 1968 by three different groups, one in Stanford by Bob Bayer and Steve Harris. They call it parametric luminescence, I believe. And then Magda and Marr at Cornell, they call it parametric fluorescence. And Klishko and Krindach in Moscow, they call it parametric scattering of light. Because the idea physically, you send one single laser wavelength in, and you have multiple coming out, like in fluorescence, in the luminescence, or just scattering of light. And then at that time, there were no confusion. Optical parametric conversion was for one type of the process, is classical conversion of light. And then this was for the spontaneous one. And then, as I mentioned to you, in 1985, Len Mandel from University of Rochester introduced this term, and it was very nice paper, open in direction, and people start using his terminology. I guess that's why it's a little bit confusing. But it has, and to distinguish this from the classical parametric down conversion, he has to put a term spontaneous parametric down conversion. So that's why the source of confusion here.
Please.
Thank you so much. This was a very informative, excellent talk. Thank you so much. I have a little question about your comment on the single particle entanglement, whether it exists or not. So this is, of course, a very old story, but into early 2000s, people were discussing about that even if there is no relative well-defined phase between these two superposition components, we can still have a reference frame independent quantum communication, violate the Bell inequality, and so on. And they decided to call it like mode entanglement rather than particle entanglement. So you have objections about these views, or can you clarify about it?
Very good question. Thank you. So you remember, you just mentioned Bell inequality violation. You cannot violate Bell's inequality with a single particle. That's it, no energy. You need to have energy of two particles to do detection of coincidences. That's the answer to your question.
Well, thank you so much, because there are very respectful people writing papers and all. This is a very interesting and confusing point. So thank you very much.
You see, I like your question very much because you see, I'm experimentalist, and it helped me a lot to decipher lots of misconceptions in quantum optics over years. On the paper, it looks perfectly fine, entanglement, right? 0, 1, 1, 0. It's a logical things, logical 0, logical 1. Right. How you would realize this? You see, you cannot, because you have to create it, you have to deliver it to the detector, and you have to detect it. And you have to detect it in coincidences. So you cannot have coincidences with one single photon. It only gives you one click on one detector and nothing on the other one. So that's it, end of the story. It's basically, it's conceptually correct, but practically impossible to realize.
I see your point now. Thank you so much.
You're welcome.
Thank you for clarification.
We have question in chat from Bugra Yalchin.
Just a second. Maybe if you can read the.
Thank you for being with us here, Professor. We have discussed producing entangled states. What can we say about the coherent lifetime of entangled states? What characterizes that?
Okay. The coherence time is defined by the structure of the process that creates this state. For example, in the atomic cascade decay, you also have two photons, and the coherence time is defined by the spectral width of the levels that participate in this process, because time is inversely proportional to the delta t is inversely proportional to delta nu, frequency and time. So in parametric down conversion, it's bandwidth of the phase matching that defines the spectral width of the down conversion, and the time of the photons will be 1 over that, 1 over delta t of the, delta omega of the bandwidth. That's all. And it's interesting fact that when you have a phase matching of the crystal of different length, the longer crystal you have, the narrow become the phase matching, which means the narrow delta omega, which means the longer delta t. So the coherence time is getting longer. In principle, you can use this to modulate your coherence lengths of your entanglement. You can have it shorter, you can have it longer. The longer crystal will give you shorter coherence lengths and vice versa. So that's how it's related. It's always 1 over delta nu of the process that created this entangled state, that defines this time.
So people thank you for this lecture, and as far as I can see, there are no questions. So if no more questions, if you don't mind, Alexander, we can perhaps close this section and stop here.
Yeah.
And we'll be waiting for you on Friday.
Yes.
Friday.
Yeah.
So thank you once again very much for being with us. That was a pleasure and honor.
Well, it's my pleasure too, and thank you very much for inviting me. And I look forward to talk to you again on Friday. Afternoon your time. And
yeah, Friday. Yeah.
All right. Thank you very much.
Thank you. Thank you.
And goodbye.
Yeah, goodbye.